Okay, so today we will discuss the fixed bias circuit, and before discussing the fixed bias circuit we will like to recap some of the concept that we have already discussed. That means why we require the biasing circuit. Biasing circuit is actually used to fix the Q point. Okay, our Q point will not change, that we have set. Okay, now fixing the Q point means your IC, the two parameter IC and VC will not change. Now if IC and VC will change, your Q point will be shifted near the transistor. Transistor, this is your load line, so your Q point is shifted towards the saturation. The transistor, some of the portion of the output waveform will be clipped up, and if the Q point will be moved towards the cutoff, then some of the output current, that means the output waveform IC, will be clipped up. So that we does not require or does not want. Okay, so that's why we have to fix the Q point. That is the requirement of the biasing. Now why the IC will change? IC will change due to the temperature. Now we have seen that if the temperature increases, three factor actually changes. First thing is your ICV0, that will changes. If ICV0 changes, your IC will change, and eventually VC will change. And second factor is your del VB. Now if VB will change, your IC will change, and eventually VC. And third factor is your beta. Now if temperature changes, your beta will be changes. Okay, and as well as IC changes and VC changes. So you will make an important out of these three. Okay, 1 minute. Out of these three, I have already said that the change in IC with respect to ICV0 will be much higher. That means change in IC with respect to ICV0. Okay, that change is much higher. So we will this is also represented by S. So this is the stability factor S. So we will try to reduce this stability factor so that we will get a more stable output. And as we get the more stable output, that means your IC will be stable, and as well as your VC will be stable. So that's why we get a stable Q point. So that is our main discussing agenda today. So for that purpose we have drawn a common emitter circuit. You can see in the circuit diagram that this is a simple common emitter circuit, and the name of the circuit is fixed bias. We have given the name fixed bias circuit because the biasing is actually given to one biasing voltage is actually used. Okay, not the two biasing voltage. Now what happens if we analyze this circuit? Analyze this circuit means we have make an KVL at the input section. So this is your input section, so you have just make use of KVL. So if you just write down the KVL equation, then what happens? VCC minus IB RB minus VB equal to 0. So VCC minus IBRB minus VB equal to 0, and from there we can calculate the IB. So your IB will be VCC minus VB by RB. Now you can see from that equation that your VC will be fixed, that means VCC is fixed, VB is fixed, RB is fixed, so your IB will be fixed. So IB will be constant. That is the conclusion from that equation. Okay, so from that equation of the input KVL loop, we can easily say that at VCC is constant, VB is constant, and RB is constant, so your IB is also constant. So that is the conclusion from your input section KVL analysis. Now from that we can say if IB your constant, okay, then we can say del IB by del IC is also 0. Any fixed term derivative of this is also equal to 0. Now if you just calculate the stability factor equation we have derived in the previous case. So this is the equation for the stability factor, 1 minus beta del IB by del IC. So this is 0, so your stability factor is 1 plus beta. So this is a quite high value. So you can easily see this is a very high value, and that is so this is a very high value which is actually not desirable, because if this stability factor is very high, that means change in IC with respect to ICV0 AC is equal to IC with respect to ICV0. So change in ICV0 with respect to IB0 is very much high. That is not desirable. Our desirable is AC is as much low as possible. So in this circuit diagram you can easily say that it is not happening. That means practical value of beta is about 200 or 100. So AC is actually value is coming 201. That is very much high. So that is not desirable. We want AC should be as much low as possible. Okay. So for that purpose we have to make some sort of changes into the circuit so that our circuit this is comes to a very low value. So that is our main agenda today. Okay, so hope you will understand what is why we make changes into the circuit so that our AC will come much lower. If AC will come much lower, that means your IC will change a very little with respect to ICV0. That's why your Q point will be stable. So for that purpose I am just redrawing the circuit here, and one thing will change. That thing is that we have to connect a resistance at the emitter section. So this is the resistance. That resistance is called the emitter resistance, RE. Okay, and also current which is flowing through this is emitter is IC plus IB. Because from the basic transistor action, all of you know that the emitter current is nothing but the collector current plus base current. So whatever current is flowing through the emitter, that is nothing but IC plus IB. So that is what all about written. And here also there is a drop, and that drop is VB. Okay, so this is all about the circuit. So I'm just first copying the circuit. Okay, so I am just again writing the equation for the input side. So equation for the input side is nothing but this is VCC, this equation. Okay, so this equation is nothing but VCC minus IBRB minus VBE minus IB plus IC into RE is equal to 0. So that is the KVL equation, new KVL equation for the input loop. Now if we just rearrange the equation, and then the equation something look like this: VCC minus IB common with RB plus RE minus VBE minus ICRE equal to 0. Okay, so this is the equation after rearranging all the term. Now in this equation, okay, now in this equation if we just get the derivative with respect to IC, okay, in the both side, then we get, I'm just changing the color, so with respect to IC, so with respect to IC, if we just derivative this VCC with respect to IC, this will be 0. Then now IB will not be fixed with respect to IC, because IB in this equation IB with related to IC. So in the previous case, whenever I have said IB is fixed or constant, so that del IB by del IC equal to 0, here this is not the case, because from that equation you can see that IB is dependent on IC. So that's why del IB by del IC is actually exist. Okay, then RB plus RE. Hope you understand this thing, why it is not. I'm again repeating that in this equation IB is dependent on IC. That's why IB del IB by del IC is not equal to 0. So VB with respect to IC is 0, and here if you just derivative this IC RE, so it will be comes out RE equal to 0. Okay, so this is the equation. I am again make this equation clear to you, that if we just make derivative with respect to IC, so VCC divided by the derivative with respect to IC, that will be 0. Del IB by del IC, this term actually exists because IB is not constant, IB is dependent on IC. So that this term VB is fixed, that's why derivative is 0, and IC RE with respect to derivative IC, that comes out to be RE. So that is the all equation. Now again I am just rearranging the equation. So del IB by del IC equal to minus RE divided by RB plus RE. Okay, so this is the equation, final equation. Now AC comes out to be 1 plus beta divided by 1 minus beta del IB by del IC. So del IB by del IC is minus RE divided by RB plus RE. Okay, so this is the case. Now S comes out to be 1 plus beta divided by RB plus RE, divided by 1 plus beta RE plus RB. Now what happens in this equation, this term is much higher than this term because beta is higher. Okay, so with this term is much higher than this term, then total equation, your S comes out to be, this will to cancel out. If we ignore this, these two will cancel out, then we are left with RB plus RE divided by RE. Okay, now this term is equal to RB plus RE divided by RE is much less than 1 plus beta. What we have, if you just calculate on your own all this thing, and the final term is S equal to RB plus RE divided by RE, and this term is much less than 1 plus beta, what we have get in the previous case. Just put the value of this and you will get a much less value than 1 plus beta. So you can say this circuit, in this circuit S is very low than the previous circuit. So just employing a RE resistance to the emitter section, we are making their Q point more stable. Hope this point understandable to you. Okay, so just making a emitter resistance here, we are just making the Q point stable. So that's why this circuit is called the biasing circuit, and the name of the circuit is called the fixed bias configuration. Okay, and our purpose of the biasing circuit, that I have already said, that our purpose of this biasing circuit is to make the Q point stable, and that is happening here. Okay, now one more thing about this RE circuit, in this circuit, that is drawback. Now what is the drawback of this circuit? Now with the transistor action, I have said that transistor is not actually operates on DC. DC is actually used to fix the Q point, and AC is used for amplification. Now whenever the AC equivalent of this circuit, what is the AC equivalent of this circuit? AC equivalent means we have to make this DC 0, all of the DC is 0, so then we get the AC equivalent. Now if we just make the AC equivalent of this circuit, then the circuit will look like this. Okay, now the circuit will look like this something. This is your RE, this is your VI, this is your RB, and this is your RC. This circuit is get from, this is your original circuit, this is your original circuit, this is your VCC, sorry, this is your RC, and this is your RB, this is your VCC. So just make this VCC equal to 0, then you get the AC equivalent of this circuit, and the AC equivalent of the circuit look like something this. Now what happens, the AC equivalent in this circuit, your VB, actual VB, that is inputting, okay, your VB here, this is your VB. Now what happens, this VB, I'm just removing this, hope you understand how to get the AC equivalent. So here in this case what happens, this VB, this is your VB, okay, so this VB will comes out to be, this VB will comes out to be VI minus IE RE, okay, this is your VB, this VB, this is your IE RE, and this is your VI, which is happening here. So this VI is getting reduced from by this value, this VB actually reduced by this amount of value. Now whenever you know the concept of the feedback, okay, so this is a feedback means this signal is actually feeding back here, okay, so VBI is actually reduces, so that is the concept of negative feedback that has been applied here. And all of you know in the case of the op-amp that the negative feedback improves the stability, negative feedback improves the stability but it reduces the gain, and that is happening here, it actually reduces the gain but its stability is actually increases. So we are making this circuit more stabilized, but what happens, unknowingly the gain actually reduces, that also we did not want. That is happening here in the case of this connecting the emitter resistance. Now how to get out of this? To get out of this we have to make, this is our original circuit, okay, RE, this is your RC, this is your VCC, and this is your RB, okay. So we have to make just a capacitor connected here. So if you just make a capacitor connected here, then what happens, in the case of the AC, that means if we just connect a capacitance, then okay, so we have to connect a capacitor here. Now in the case of the DC circuit, all of you know that in the case of the DC, capacitor will act as an open circuit, okay. Now in the case of AC, capacitor will act as an short circuit. Now in the case of the AC, the capacitor, as the capacitor will act like a short circuit, so this emitter resistance will have no effect onto the circuit because all of the current will be bypassed through the circuit. So actually the problem that is arising here, that problem will be eliminated whenever you consider the AC equivalent, because the AC equivalent, that RE resistance actually vanishes because RE is connected with a short circuit path, so all of the current will pass through this short circuit path, okay. So just connecting a capacitance across here, we have just eliminated the problem that is arising here, okay. So hope you understand the point, the advantage of connecting the emitter resistance to improve the stability, and later we find that if you improve the stability, then the gain is actually reduces whenever you connected AC. Now just by connecting a capacitors across this, we have also eliminated the problem. So that is the complete circuit. So this is your RC, this is your RB, and this is your RE, and the capacitor connected across here, so that we can faithfully amplify the signal. Hope you understand this. Thank you.